Good morning, everyone. Please take a seat and let's get the show on the road. So yes, good morning. I hope Svalbard treated everyone well yesterday and you managed to sleep at least a bit. Nice weather today as well. Remember, roads are slippery and they're gonna get more slippery today because the temperature has risen quite a bit during the night, but still nothing major. This morning's program is going to be 2 plenary sessions with a coffee break in between, and we should break for lunch at 12:20. And let's not be late. 2 reasons. One of them is that the cantina will want us to be there when we said we're going to be there. And the other thing is that we will have the bus transport to SeaSAR right after lunch. So if we are late, we actually eat into our lunch. We can't postpone the departure to SeaSAR. Yeah, that's yeah, you can leave them here.
Because you're all coming back here.
Yeah. Yes. Yeah, no, just leave them here. That's good. All right. So without further ado, it's the Doppler shift gang that's gonna have the first plenary of this morning. So stage is yours.
Okay, then can you start the presentation?
This one, right?
Yes.
There you go.
And this mouse, okay. Okay, good morning. Welcome to our session on Doppler retrievals. I'm Roland Rohmeiser of the University of Miami. I'm sharing the session with, what was that? Okay. I'm sharing the session together with Artem Moiseev of the Nansen Center and Paco Lopez-Decker of TU Delft. And I will present the first part of this main plenary session presentation, which is a review of some major things that have been done in the last 20 to 30 years. And then Artem will talk about some Sentinel-1 Doppler retrieval activities, and Paco will talk about the really complicated stuff with modeling and calibrating the data. And I want to start with this because this will be a topic again today, modeling of Doppler signatures at high resolution. This is from a paper I published in 2005 based on experiments we did in, I think, 1999 and 2000 or 2000, 2001 with this German airborne long track INSAR. And so we had, in that case, only a single beam long track INSAR looking sideways. And we flew here at this reef in the North Sea in 4 different directions to measure 2 components of the current vector. And then we had an initial velocity field here. Can you see my mouse pointer there? Maybe not. So we had this initial, can you see that? Yes. We had this initial 2-dimensional Doppler velocity field. And then we had a iterative correction scheme here with a numerical long track INSAR model to compute corrections for wave contributions and their spatial variations due to wave current interaction. And in the end, this was our best result for the true surface current field. And here are the differences between the input and the output current fields. And we were able to show by comparison with model results that our corrected current field was better than the initial Doppler velocity field. So this was done about 20 years ago. We will still discuss today how this should really be done and how it can be improved because it's still not good enough. but it's interesting to see that we already did something like this 20 to 25 years ago. Then here, I think this is more or less the last thing I presented at this meeting here 20 years ago, our first long-track INSAR results from space based on the space shuttle data here from the SRTM mission in February 2000. This was also published in 2005. So here's the space shuttle with the SRTM external antenna, and this is a line of sight current field that we retrieved from the data, and this is a corresponding model result from a Dutch group. And we found good agreement, and we found that the accuracy of 0.1 meter per second at 1 kilometer effective resolution was consistent with what we had expected from this kind of system, which was far from optimal in its parameters. This was not designed for current measurements at all, but it allowed us to demonstrate for the first time current measurements from a satellite using a long-track interferometry. Then we got into the age of TerraSAR X and Tandem X, the two German satellite missions, and our TerraSAR X here, which was launched in 2007, has this 4.8 meter long antenna panel that can be divided into two halves to do divided receive antenna operation for a long-track interferometry. Again, far from optimal in its parameters. The antenna halves are way too close to each other, but this was good enough for some more demonstrations with a similar quality as we got from SRTM. And then in 2010, the Germans launched the second satellite, which is flying in close formation with the first one. They are actually circulating around each other, and you see a diagram here that shows how far they are typically apart in a long track direction at different latitudes. And there are only some small windows where the distance is good for current measurements, but we were able to use those windows and some special mission scenarios to demonstrate current measurements with that as well. Here's a paper from 2014 from the Pentland Firth here at the Orkney Islands, northern Scotland. Test area size that's shown here is 30 kilometers squared with a grid cell size of 25 meters squared. And here the first velocity image here in the middle is what you get from the divided antenna mode at this resolution here. You see some signatures of the current, but they are very noisy. Then here on the right, you see what you get from the Tandem X here with an effective baseline of 25 meters, which is near the optimal baseline you would wish for current measurements. And you see that without any smoothing, any noise reduction here, we can even resolve the swell wave motions here. I will come to that in more detail on another slide. You can improve the quality of the divided antenna mode data by smoothing. Watch what happens now when I push the button here. It smoothes itself, so now it has less noise in it, and it is usable, but at a much lower effective resolution than what you can get with the longer baseline from Tandem X. So the sensitivity in the two cases are here in the middle image there from divided antenna, you have 200 meters per second over a 2 pi phase interval, so a very low sensitivity, while with the Tandem X you have only 9 meters per second within 2 pi, so you have much stronger phase signatures for the same kind of horizontal velocity. Some more things we did with the Tandem X data. This from the same image here. We calculated over how many pixels you have to average here to reduce the residual noise in the data, the residual RMS variability. And in the case of the dual receive antenna mode, you have to average here over more than 100,000 samples. In the other case here, only over a few 100 samples. That corresponds to an effective grid cell size of 1 kilometer squared in the case of the simple divided antenna mode, and 1 square kilometer, 33 meters squared, so a factor of 1,000 in terms of area size improvement with a better baseline of a Tandem X to achieve the same residual noise at a factor of 1,000 improved effective area size. We also had an experiment here where we acquired a series of images while the two Tandem X satellites went from the southernmost point of the orbit northward, and the south they are usually on top of each other, and then when they go north they slowly move away from each other, so you have an increasing long track baseline. And that enabled us to study the coherence as a function of the effective baseline. And you see the results here. I don't want to explain them too much, but the black stuff here with arrow bars is what we got from the data. The colorful lines behind are theoretical model predictions, and basically we show that our data are consistent with model expectations. Some additional explanations there why it doesn't go all the way to 1 and 0 at the beginning and at the end due to some issues that were not unexpected. We also analyzed here the effective number of looks for ideal data with independent data in the pixels. You would expect the number of a little more than 100, like 120 samples to be sufficient. If you average over 120 samples, the noise should go down to 0.1 meter per second. In fact, we need to average over 470 samples here, which is because the data are not completely independent. They are oversampled. And so you need more samples to really reduce the noise, but that's a separate issue. That's not really so relevant for our discussions in this meeting. Then something I got from Paco Lopez Decker yesterday, kind of artist's impression there of his experiment. He was at DLR at the time, and Paco, I put it here. I hope that's okay for you. So he had access to Tandem X to do some crazy things that normal people like us were not allowed to do. They did this experiment with squinted beams where one of the satellites looked a little bit, or how was it done? One satellite looked a little bit ahead and the other, or was it, or did you just divide the beam in some way? Yeah, was it? Yeah, so they did not rotate. They just had the beams steered like that. So as a result, you have two beams that are slightly apart from each other going in two different directions, and that allows you to measure radial and azimuth components of the velocity with a much better sensitivity to the radial component. But this was good enough to see some azimuth velocity here, and if you put that together, you get a vector surface current field. So this is already similar to what some future instruments will be able to do. Of course, they will be able to do it better, but Paco demonstrated this already many years ago with Tandem X, and I think he will talk more about these things in his own presentation. Then here is something we got yesterday from our friend Gordon Farquharson in the United States, whom both Paco and I have worked together at some points in our careers. This is from an experiment that Gordon and I had together in 10 years ago at the Columbia River mouth in the northwestern United States. Here you see his long track INSAR, which is a dual beam long track INSAR under a little Cessna 172 and some other instruments. And here are two examples of vector current fields at two different tidal phases. These may still be, I think these are still the original Doppler velocities, and then he had a PhD student using, I think, my numerical model actually to do the same kind of corrections to get the surface currents out that I had tried to do 10 years earlier or so. So that was already done 10 years ago. Then here we are now going to Anis Ilyunsha from Gothenburg, who may want to give his own presentation in our breakout session, but I included this here in my presentation. This is from Tandem X, an intensity image here on the left, and then the initial Doppler shift. From the Tandem X phase. And here wind vectors to compute corrections. This is at the Agulhas current. You see surface temperature here, and you see a model current field. And on the next page, he shows this is his original radial velocity field derived straight from the data. So this is the Doppler velocity. And then he has two solutions here corrected with different geophysical model functions for the, or different models for the Doppler correction for the wave motions. They look very similar. Here you see the difference between the two. One of them seems to be a Ka band model. I'm not sure how that exactly is applied to X band, but well, the other one maybe for C band. He will explain that more when he gives his presentation. So anyway, so there is some experience with that as well. Then the next topic in the presentation should be Doppler-centroid anomaly analysis of single antenna SAR data. This had already been started when we were here 20 years ago, and the French team, and maybe, I don't know if the Norwegians were involved already, they presented some of the stuff. They were doing it with Envisat. We don't have contributions from them for this presentation here, but when we write the white paper, I think we should give an update on what has been done in that field in the last 20 years as well. Then
of Envisat SeaSAR data from 2002 to 2007.
Yes.
So that has to do.
Yes, we will talk about that in the breakout session. Then now they are doing it. Johnny and my co-chair Artem are doing it with Sentinel-1 data, which have their own difficulties. And Artem will talk about that. I was not ambitious to put something into my presentation. He has a whole presentation on this following right after this presentation. Then we got this from a French team. This, you will also see this again in Artem's presentation. And the authors may be here. I don't think I know them in person, but they may be here to present this themselves. So there is something going on here with the comparison with HF radar data. I will not talk much more about it because we will see this again in other presentations. Then I wanted to show you this. Some of you have seen this already. This is something I started to do a while ago, maybe 8 years ago or so. It's not so much about currents in this field, but you can use it for currents. We have this spotlight mode, sliding spotlight mode in this case, a Terrasar X image of this area around this island in Australia, where you have the wave patterns, and you can, because it's a spotlight mode image, it has a long integration time. You can decompose it into a series of subaperture images that enable you to see wave motions, and then you can filter the visible wave patterns using fitting the dispersion shell according to the theoretical dispersion relation. And you can remove everything that doesn't behave in the way linear wave signatures should behave. And here on the right, I show the moving wave patterns. This is for a longer time than the actual integration time. So you see the wave motions better, but you see there are some realistic looking wave motions with realistic looking refraction patterns. And in the process of fitting the dispersion shell, you have as the fit parameter the water depth. And these are the water depths that I retrieved in this case, which are somewhat consistent with the known water depths in the area. That's not our topic today to talk about water depths, but this could in principle be used for vector current retrievals as well. And so this is a little outside the usual things we will discuss here today and tomorrow, but since this is something I have done, I think it's exciting. I thought I smuggled it a little bit into this presentation here. Then let's quickly talk about future missions. So here is the SeaSAR mission proposed by Christine Gomen-Ginger, who unfortunately cannot be here today. Maybe she is online and she can talk about it in our breakout session. So this is a dedicated satellite mission with a dual beam long track INSAR for high resolution surface current retrievals in here the coastal and shelf seas and marginal ice zones. They have worked on this for many years. They have done airborne experiments. They have done all kinds of studies, and they are still trying to convince people that this is the best Earth Explorer 11 mission. So it has already been selected as one of the candidates, but there are still some investigations going on. And this is certainly one thing we need to discuss a little more in the breakout sessions. What is the potential of this, and what are the remaining challenges to be solved to get really good data from this kind of system. I will not go through all the there. You can read that yourself. Here is another slide that shows a little bit how it works. So you have the two antenna beams here looking ahead and looking behind to do dual beam along track interferometry to the side here, and from the combination of the data you can get vector Doppler velocities and then vector surface currents, very similar to what I already showed you there from the airborne measurements by Gordon-Farquharson, but now this will be on a satellite. And then there is another one that can do similar things, the Harmony mission with our expert Paco Lopez-Decker here. And again, I left out the slides for that because he will talk about this excessively at multiple occasions in this meeting. And finally, I wanted to mention this because I think it is important and it will complement the SARs. This is not SAR, so we can say again, this doesn't really belong into the session, but we are talking about Doppler scatterometers that are like an extension of the wind scatterometer missions that already exist, the American ones and the European ones, with Doppler capabilities. So instead of just getting almost global wind fields at a few kilometers resolution every day, you get surface velocities, surface currents with the same resolution. And of course, the knowledge of the currents will make the wind product better. The knowledge of the wind will make the current product better. And there are several papers here. The Dutch team here had an idea how you can do it in the European style. Then there was a group around Ernesto Rodriguez who published a 59-paper study, 2018, on how it could be done with a rotating pencil beam like the American QuickScat and those instruments. Then this developed into the American concept vacuum. And then I heard at a conference last year that now it's called Odyssey, and it's a US-French partnership. There's also something independent going on, I think, in Europe. Maybe we can talk about it a little more. Maybe if Ad Stoffelen is still online, he can say a little more about that in our breakout sessions. In my opinion, the combination of these low-resolution global Doppler velocity vector currents from the scatterometers with the high resolution stuff that the along track INSARs can do using the same imaging mechanism and sensitive to the same wave motions and so on. I think that will be fantastic, and that will really make a lot of sense to have those two types of instruments together. And there we are, more or less 20 minutes that I wanted to speak. I think we have time now to discuss some questions, if people have questions about this stuff. And then we go to Artem's second part of the presentation. What should I do now? Should I hit exit to, yes, to see if there are, yeah, there is already something here in our chat from Marcos Portabella. So Oscar, the SeaSAR prototype, is currently flying over the Mediterranean, benefiting from the SWAT campaign. That's very nice. Further questions from the audience here in the room? Questions or comments? Complaints? If not, maybe we can immediately continue with Artem. And we can, if you have some new ideas, we can still have another discussion after Paco's presentation, right? So I take this microphone off.
Hello? Does it work?
You have your own one? Oh,
yes. Okay, it does work. So okay, yeah. Thank you, Roland. And I prepared the second part for this plenary presentation, which is going to focus on the Doppler retrievals from Sentinel-1. So not like all the future beautiful Doppler missions, Sentinel-1 is flying right now. And we've been doing quite a lot of work, not only we, but a lot of colleagues on different aspects, so in trying to retrieve meaningful and reasonable geophysical parameters from the Sentinel-1 Doppler. And today I'm going just to briefly cover several things related to the work being done in the past years and potential for the future of this data. So, and I would like to start here. So with Doppler centroid anomaly, and this equation should be way more complicated than that, but for simplicity, we just say that it's given the perfect calibration and perfect data. The Doppler centroid anomaly of the ocean is a combination, sum of sea state contribution and the ocean surface current contribution. And if data is perfect, that's the only problem you have is how to partition and interpret this data. And that would be nice, but as soon as Sentinel-1 was launched and people started to look into the data, they realized that the equation became a little bit more complicated right away because there is a whole range of problems with the instrument which must be addressed before actually going and tackling all the geophysical issues. These issues related to the unstable satellite attitude, some bias, scalloping signal we have, some antenna temperature compensation, and there is some delta put in the end because potentially the longer we look into this data and the better we get in calibration, maybe some other things emerge. Meaning that in order to provide some reasonable geophysical analysis of this data, we face 3 challenges, which I'm going to cover today. And the first challenge is going to be related to all this right-hand side part of non-geophysical contributions, which must be carefully evaluated, estimated, and removed. And after that, we actually can jump into the analysis of a geophysical signal and try to partition them between sea state and current and whatever other contributions we would like to see. And then something about how we actually going to try to use this data and what's the potential of usage of this data for the remote sensing and for the other communities. Yeah, so I have some examples on that. So here are some sites I received from the people who involved actually more directly in calibration. So here's it's only Gilles' name on the top, but there are several more people involved from NORSE, from Ocean Data Lab, from SeaSAR, and from ESA. And on the top here, you have a quick history of what was happening. And we know that in 2014, the Sentinel-1 was launched. And there was a calibration strategy proposed based on the attitude orbit control system and antenna model, and it didn't work at all. So from evaluation I did back in time, we had errors of about 8 hertz in precision, which is ridiculous numbers if you want to go and study ocean surface currents. A few years down the line, it was a little bit improved, but still not working very well. But 2018 is the year we were waiting for, and we are really happy about, is because there is a new calibration strategy was proposed, and base for it was the gyroscope telemetry was available, and then there's a new calibration approach was developed by the whole group of people, and this is something we're using now, and I think it's going to be improved in the future. And yeah, now as mentioned, there is a plan to generate a new large calibrated data set and hopefully make it available for the large public so we can go and look on all the other things we can do with this data. So practically the new or current calibration strategy is based on the Doppler, which partitions to 2 contributions, one from attitude, which includes fast attitude variations, and slower attitude variations, which we learn from the data, but and also the bias, which is related to the electronic mispointing, thermoelastic effects, and mean attitude error. And DC bias also, we know it depends on the acquisition mode, so we have different ways to estimate it from wave mode and for IW mode. So important part here exactly is that a lot of calibration is relying on the observations. So we look in the data very carefully and we try to so learn and see what we can get from this data. And yeah, so how to move on from it. So a little bit more on it. So we have this on the top panel, we have DC attitude. Doppler centroid attitude. So we see on the left part of it is so information you get from the gyra is a pitch deviation in millidegree. And on the right-hand side, you'll see corresponding the Doppler centroid. And you see quite nice agreement between them, especially it's really spot on around this. Okay, you cannot really see this, can you? Yeah, okay, around this, you see this very strong features, especially like right in the middle of a figure, so you can see something very interesting. So there is also a very interesting point that 1 millidegree of error in a pitch will give you error of 5 Hertz, meaning that there is a very strong requirement of a precision, and we have to go and actually accurately remove and estimate these things and also take control of it in the beginning. So maybe we can do it even better. But we also have bias, and you know, interferometric wide, it was really shown that for the bias we can use length observations, and in general, length observations are quite commonly used for evaluating the signal and estimating the errors. And yes, so what else? So here we also have, yes, so on the bottom slide you have Doppler centroid bias over 1 month of wave-mode observations. So, and here you can see also very interesting jumps between different parts of a signal, which seems to be associated to the change in Vancouver pair of star tracker used for the satellite. So here is just another example of what we were estimating over the land, is that also from IW data. So practically on the left-hand side, you see this bias. So something we, in the beginning, was proposed to use from using antenna model, which is in the red curve. And the blue curve is something you see from the observations, and you see that they don't agree almost at all. So that's why we need to look into the data and to estimate this calibration. And on the right-hand side, you also see some scalloping signals and the attitude variations along the orbit. And a lot of it is now corrected thanks to this new calibration which is provided. And one of the very important points here is that the residual Doppler, according to our estimates, after this new calibration is about 3 Hertz, corresponding, if we would like to go and try to convert it to orbital velocities, is about 15 to 25 centimeters per second, which is about 2 times improvement compared to what is available in the beginning, which is really great. And it's not done by any means, so there is a lot of work still to be left, but it's a major progress, which was done since the beginning of the mission by the group who is involved in the calibration. I believe we're going to have more about it in our breakout sessions, but it's really a nice result, which actually allows us already now to go and to look into the geophysical signal, even though we obviously would like to have it even better. And last part of the calibration is something related to the next challenges. So here on the scene in the middle, you see this very interesting jump in the Doppler, which is related to antenna temperature compensations, which is an issue we see in the signal constantly or quite often, and it's still something not tackled very well and something we would like to see in the future being addressed. And about the future, there is a really interesting thing going on because, is it still working? I'm not sure. Yes, so there's some interesting thing going on because there's going to be, well, Sentinel-1B is gone, unfortunately, but there's going to be Sentinel-1C launched. And Sentinel-1C, not like A and B, has a different system. So it has a new star tracker and a new gyro, which here is claimed to be less good gyro, and we believe in it. And this is something which is going to become an issue. Hope potentially in the future, because something we learned into the data and developed over years, might be redone again. And so this is something which must be addressed in the future and also for the next generation missions, and the configuration and the instrumentation for the star tracker and the gyro must be aligned in the requirements according to what we need if we would like to actually go and retrieve some meaningful measures from the Sentinel-1 Doppler. So enough on calibration for now. I again believe that we're going to have more detailed discussion about it in our breakout sessions. But once we tackled all our non-geophysical signals, there is going to be a second challenge, is the partitioning of a signal between different geophysical contributions. And so personally, I'm interested in ocean surface currents. And if you're interested in ocean surface currents, you will say that the sea-state Doppler is something you would like to estimate and remove, which is not the case for everybody, but it's still something we learned from the data. So practically a contribution between sea-state and the ocean current. So the approach was previously developed based on actually Envisat data. is something called SeaDop. I think it's quite widely used by different people right now for the experiments. And the idea is pretty simple, is that you get your wind fields from collocated models. So there it was ECMWF. You have wind speed, direction, you have different incidence angle and polarization. When you train your geophysical model function, and then you predict sea state and remove it from the signal. And it was a really nice idea, but there were some issues with that. So on the right-hand side, on the top slide, you have the simulation we did just for different wind speeds, and we see that it provides some really, some artifacts which we would like to address and remove, especially around 0 meter per second wind, which gives us sometimes up to 10 Hertz Doppler, for example. This is something we would like to correct for. And inspired by this SeaDop idea, which was really nice, we decided to advance it in the future and account not only for wind, but also for wave contributions from wind, sea, and swell. That's how the SeaDop 3.6 was born. And so from this, again, simulation on the right bottom slide, you'll see that there are some readjustments and improvement been done. And it really helps us, at least for now, with this very simple method to better get account to the sea state Doppler, which in future we believe will be improved. So here is just a simple visualization, how it look a bit more in practice, where you have wind, sea, and swell fields on the left 3 panels. You have some kind of reference for surface current, which is a model. So we don't really use it for validation, but just for comparison, just to make sense of 2 different data sets. And on the right-hand side, you see the Doppler from Sentinel-1, which was not before the calibration. So that's why it looks a little bit strange. And so what we have to do, we have to calibrate it. We have to feed these fields into our GMF, remove it, and get the surface current. And here is the example of it. So the calibration signal is on the left-hand side. So it looks very different from what we see on the previous slide. So the next one is the old approach, was developed for NVSAT with SeaDop. So it's surface current, which is estimated using the SeaDop. So after removing the SeaDop prediction from the total signal, we start to see the Norwegian coastal current. We know it is Norwegian coastal current in the bottom next to the land, but we also see some artifact, especially in the near range. And then there is some consequent improvement of this with using our new geophysical model function, SeaDop 3.6. So it seems from there that accounting for different contributions, not only from wind, but also for the sea states, indeed helps us to improve the geophysical retrievals. And it's also particularly important in the coastal zones where we know that fully developed sea concept is not working that well anymore because of the fetch limitations. And then we would like to actually have a direct information from the sea state. Well, now it's from the model, but in the future, it's going to be different, which I show you a little bit later. This is just an example that it's not only activities on IW, we also use wave mode observations to develop some solutions for the global open ocean. So this is, I believe, 0.5 degree grid, or based on 2 months of observations, just like some experiment we did back in time. So, and again, so on the right bottom, you have drifter climatology, and on the left bottom, you see the product we developed back then, which actually since then was already improved. So, but yeah, still we see a lot of similarities and some quite interesting potential for monitoring equatorial currents, for example. Okay, so I probably should speed up. So the issues with these GMFs is that, yes, so now we see improvement, but we're still using the models, and using the models have several problems. One problem is related to the fact that the models are maybe just not good enough. I'm talking about wind and wave models. And we actually don't want to use these model observations to correct our data. And that's inspired us to develop this new solution based on the SAR cross spectra and actually utilizing information directly measured in SAR in order to correct and retrieve information about ocean surface current. And in this, I think also mentioned yesterday, the discussion about simultaneous retrievals of wind, wave, and current properties from SAR should be also addressed. And I think we're going to have a discussion about it hopefully later. So based on this new calibration in our geophysical model functions, we came to developing products. So this was available thanks to the ESA World Ocean Circulation project we're part of. So we were actually able to produce 1 year of observations Here is for Agulhas current, but currently we have an activity to extend this data set to also to Norwegian coastal zone, to Orkney Islands, but potentially also like to the whole North Sea. So this is something is really nice. So now it's allow us to actually start looking into observations more in terms of a geophysical signal, but also something we can learn from developing this product and evaluate it and maybe validate it and then come back to the challenge number 1 calibration and everything and redo it again and improve hopefully in the future. We did or kind of validation, it's not really a validation exercise, but just a data cross comparison when we have surface current from Sentinel-1, we also have geostrophic currents from Avisa, we have some sea surface temperature, and we start to see quite interesting similar features, especially in terms of eddies. Here cyclonic and anticyclonic eddies and the main Agulhas current. So this is coast of Mozambique, I think. And so we also see that if you look into the Mercator model, there are some features which remind us of something we see in observations, but as expected were a little bit misplaced and mistimed. So just demonstrating the potential of the Doppler observations for the validation of your model products or other products and the cross comparisons. Just to come back or move forward rather on validation, there are some exercises we did using high frequency radars. And the idea was that high frequency radars are regularly available, which makes them really nice, even though sometimes they're not so great. Some of them are not very well calibrated. But there is also a question of the depth of the measurements, which also has to be addressed. But generally, it was a very first exercise done some years ago when we compare radial velocities from one beam of HF radar with similarly directed surface currents from Sentinel-1. And what we see is some reasonable agreement back in time. This was done also before the newest version of the calibration, so we expect it to be better right now. It's something we have to redo in the future and put some effort in. And also we do some comparison with drifters, and back then we claimed that that was actually the best way to compare, which existed, some very shallow drifters, or not very, but so it's Carter drifters, like 40 centimeters or something. So at least from data available and something practical is something we can use in the future. And so after that, there were several other activities. So there was a paper by Adrian Martin on the multi-year assessment of a Doppler from Sentinel-1 using HF radar. And then we have contributions from Baptiste here, and he's here. So he'll be participating in the discussion. And this is just an example of evaluation of the Doppler velocities from Sentinel-1 using HF radar systems, which also shows some quite interesting agreement. And again, there is something we have to put effort into using this data and try to figure out what the differences are and how we can take advantage of it in the future for more systematic validation exercises, potentially, or at least cross-comparison exercises. And I would like to finish my presentation by just this example, which was prepared during World Ocean Circulation by the Ocean Data Lab. And this is just a simple example which hopefully will demonstrate the value of using Doppler observations for model validation and product validation. So here we have a background field, which is a high model surface current. And this SWOTS is Doppler current we derived from Sentinel-1. And so here it seems quite disagreeing. But when you start to look into the altimetry, you start to see more agreement. It's a standard Siemens product. When you start to look, so this is another work product, which is improved because of geostrophic currents. And so, yeah, so here we start to see really, really nice agreement between features in Agulhas current and reflection between two products, which start to be really nice for us to make us believe that we may be doing something interesting and this is something should be exploited in the future. And this is, again, coming back to now to Mercator 112 model, which is provided by Siemens, and where we start to see a lot of disagreement as well. So there is a lot of potential in Doppler observations. We would like to use them in the future for many things, for the calibration and for validation, for example, purposes. They can be really useful. But again, there are several things which should be discussed and addressed in the future, and in the future missions as well, regarding especially the system for calibration and the instrumentation we have. We also will have hopefully better improvements in the sea state estimations, or signal partitioning. I think Paco has a lot of slides on it to explain it in more details, in something which potentially can be done. And yes.
Not have the positive, negative velocity field.
No.
But your radar has.
Yes. Yes.
Hence, the comparison is a bit unfair to the model.
Yes.
So you need to, if you want to use those kind of slides for validation, you have to correct for that velocity direction and see.
Most certainly. But what you can see quite clearly is that once you start to see features, you see the features. And if you see here the feature of main Agulhas current going this direction and CMIMS going this direction, the projection of the data is not going to change much. Yes, this is the current going in the opposite direction. And yes, so you're right. It's maybe not, yeah, it was a bit of a lazy work. So I had to reproject it and prepare a figure differently. But it's going to be totally addressed in our future versions of a presentation. So that's, thank you very much. I think I'm going to finish on it. If you have some questions on the Sentinel-1, so we have a few minutes maybe to discuss them. And then Paco will continue to his part of the presentation. So, some questions? No?
More questions.
We need most certainly more questions. Yes?
Thank you, Artem. Well, it's nice to see that Agulhas, but did you try to look at other places?
Yes, most certainly. So our initial activities, like I'm working at Nansen Center in Bergen, so we're actually very interested in the Norwegian coastal zone. So we have a look at the Norwegian coastal current, which has velocities ranging between 30 centimeters up to probably 1 meter per second in really strong scenarios. And we, especially this comparison we did with HF radar, was for this weaker current regime, and where we still see quite a good agreement, and we see a lot of signal. So obviously, when we're talking about 3 Hertz precision in the Doppler after calibration, we start to be really cautious about what we can quantify and how weak the current can be. So we still believe that it should be 20-30 centimeters per second to be meaningful. But so yeah, clearly in Agulhas, of course, we love Agulhas. It's really strong current. We see everything very well. It's a lot of observations, but yeah.
Can you use the microphone?
I'm sorry. You show in the Agulhas this very nice comparison, but I think we should have very prepared data for the modeler, for example, to do some validation on this part. So I think it's really not easy to
Yes,
to check directly. So you are used to work with this comparison, but providing this, it's really important to ocean modeler to focus on this comparison and then how they can improve their model and also their assimilation bar. Basically, this is can be captured by the assimilation. So.
Yeah, sure. So this is a part of a work project we are part on, and this is one of the action we have right now is actually to try to provide a user-friendly product. So it's we call it level 2 ocean surface current product. So which is based on something I showed you before in this particular product, but also make it more, in terms of data formats and everything, more usable for people. Because, yeah, I think you're absolutely right. The data formats and everything should be changed to make it more useful.
Thanks, Artem. It's really great to see this development. And I think you said it, but it can't now be more emphasized. And the fact is that the imaging radar now, we have worked with the normalized radar cross-section for 30 years, and we have known that the normalized radar cross-section is a combination of the contribution from all contributors to surface roughness. So predominantly the wind, the waves, and the current. And what we are starting to see now, thanks to the use of the Doppler, which is a new addition to the surface roughness, and is that we are able to breaking now the contribution to the roughness into the wave contribution, the wind contribution, and the surface current contribution.
Yep.
And this is a very a promising approach to a completely new way of managing the use of this imaging radar system. So it's really nice to see this. And we have a question in the chat.
Yes, so how do I... Or maybe she can... Can I? Oh,
Can I say something?
oh yeah. Yes. Hello.
Ah, hello. Hello. I've been able to unmute myself. Thank you. Hello. Good morning, everybody.
Yeah.
I just want to pick up on what Johnny just said about these contributions from waves and currents and everything, and particularly Artem. I think during this meeting we need to be very to agree on the terminology of what we're actually talking about, because C-state contributes to the signals we measure, both in terms of the modulation of the scatterers, which is registered by the radar, but is not actually a current, and the contribution of C-state to currents in form of Stokes drift and other things. And people are really interested in Stokes drift, right? I mean, that is one of the contributions that you cannot measure, for example, with altimeters. So it's really important that we clarify what it is that we mean. So we can't just separate things into C-state contributions and currents. We have to be very clear about this. So hopefully this week we can agree on the terminology, on what we are calling this kind of effect, which is simply an impact of the scattering mechanisms. I mean, I say simply, it's not that simple, but it's an impact of the scattering mechanisms as opposed to the physical contributions of C-state to the current, to the ocean circulation.
Yes, thank you very much. Yeah, I think it's at least in terms of agreeing on calling things the same way for everybody, I think it's great. And also, yes, exactly to the Stokes contribution and what we actually calling the C-state bias. Yes, I think it would be a really nice outcome if we could all agree on something and move
Please
on
don't
to
call
get
it
ready.
C-state bias. Please don't call it C-state bias. It isn't.
Okay,
That is going to introduce so much confusion. C-state bias is a very specific error in altimetry. Please do not call it C-state bias. It's not a bias, and it's really not C-state bias. Thank you.
Okay, yes. Okay, Paco?
I don't know this thing.
I like this.
This goes over the ears, it is?
It should work.
Okay.
I think there's another question.
There is no question. Okay.
So,
Okay. Do I have this thing now correctly? I don't think so.
yeah, so the question is from Adrian Martin, that is there any plan to reprocess the Sentinel-1 data?
Okay.
It's not going to be a short one, is it?
So it's a really good question, and I think this is something I didn't mention during my presentation. That given that the Sentinel-1 would be a nice continuation also of something was done for Envisat before, so it would allow us to build a really longer time series by now to start to look on the geophysical signal. It would be great if we could reprocess the Sentinel-1 back in time, back in 2014, but this is something should be addressed and I think should be discussed, but I think maybe there is in auditory people who are more skilled and experienced in that and could address this question. Someone? Reprocessing of a Sentinel-1? Anyone? So that at least, yes, should be a recommendation to ESA to go back in time and reprocess it to the archive. And I know that it can be challenging with new calibration, but this is something we should require quite strongly so we can go and actually make the useful product in terms of temporal coverage as well. Any?
So while they are setting up,
Yeah.
maybe you can say something also about the Doppler. You present the Doppler from Sentinel-1, which is VV. What if we have quad pole data, and what will the Doppler signal be? How would the Doppler signal be valuable for quad pole data?
That's a good question, and since Paco finished setting up, so he probably will address it to some extent in his presentation, and I will give floor to him because we're a little bit over time now, right? Fine?
I think we're fine. You hear me?
Yes.
Okay. Yeah, I will maybe talk about that, maybe. Okay. So let me first spend a couple of words on my view on this workshop. So I think we tend to go around showing each other how good the stuff is, how good is what we do, right? We go to places, we show this is great. I'm PI of Harmony. Harmony is a great mission. Implement it, right? And that's what we typically do, right? We show how good the stuff is that we are doing. And coming to Svalbard, and the format of the workshop, I thought this is an invitation to try to do the opposite, right? Try to tell each other how problematic everything is, find the problems so that we can discuss them, right? Because we are the SAR community, right? So we do not need to promote the use of SAR because we are SAR people, right? And when we can be honest to each other, right? It's okay to say, okay, this is what we don't know. And I think that's what we try to do. So I thought, okay, I'm going to try to explain how poor our understanding is of the wave Doppler, which is my term for this. And to do that, I was reviewing what we are doing, and I'm guilty of if the understanding poor is I'm part of the people not understanding it well. But to prepare this, I went back to the literature and tried to read what we have implemented in our simulators. And of course, what happens is that when you start reading, then you start to think that you actually understand it. So then I found myself preparing a presentation where I was going to explain to you how things work. And this is probably good, because now I'm going to try to explain to you how things work, but I don't really know. So what you will get is a lot of confusion, and then you may think, okay, the guy doesn't understand anything. But hopefully, the impression that you will get is that we don't really understand everything. And that's good, because that would be the key message. And you should interrupt me, and if you disagree, that's good. Because then you disagree, you tell each other, and then we can discuss, and then I think we are achieving the goals of the workshop. Okay, so that's the setting. And this is a bit how I see that we have that our understanding has evolved of the wave Doppler, and I'm in the privileged position that I can call it the wave Doppler, and because I'm PI of Harmony, and Harmony will fly, and it will be the first mission that is really dedicated to measure Doppler from space with multiple directions. Then if nobody convinces me of something else, I think we will more or less impose the terminology to the rest, but I'm open for better names. I think wave Doppler is a good neutral term. It's not a bias. But this is the understanding of the wave Doppler. And the wave Doppler for me is the main thing that we have to deal with. So the currents themselves, if you get rid of system errors and of the wave Doppler, it's a very geometric thing to measure, so it's easy to get, right? The difficult part is to get rid of the things that you don't want to have, in this case, the wave Doppler. And somebody understood years ago that you have that the slopes of the surface and the motion of the surface due to waves are correlated with each other, and because the slopes are modulating the backscatter, you have a correlation between the backscatter and the instantaneous velocity of the surface, which causes a Doppler, because it's an apparent velocity. And in the old understanding, it looks like as if the surface is going up because of this coupling between the vertical motions and the backscatter. And so years ago, we understood that there would be a Doppler linked to the waves, which are mainly driven by the wind. So we could expect to see the wind signature in the Doppler. Now, around 2000, our friend Roland and his colleagues, they actually developed a nice theoretical model for that, which is the grandfather of all the models that we have right now. Because in fact, if you look at what we are doing now, we are trying to improve on what they already did significant time ago, and other people, not only him. And a bit later, we started to have empirical models where you could have we had lots of data from EMISAT, from ERS, and so on. And we could try to link the wind that we had from models and from measurements to the Doppler that we were observing in the data, and with that developed the first empirical models for the Doppler. Now, as time goes by, and if you go to recent years, what we are seeing is that there's more stuff in the Doppler than just wind-driven waves. And what you see is that models are adding stuff to it. In particular, an important thing that I think came in the last years is the contribution of breaking waves to both backscatter and Doppler. We're trying to model that. And what's nice to see is that also, if you saw the previous part of the presentation by Artem, also from the empirical point of view, people are looking at other contributions than just the wind. So looking at wave information, and if this presentation had been 6 months from now, maybe it would have been even nicer, with better wave information extracted from the data. And if you listened yesterday, I think if we continue this way, then the next station is to have this integrated view, multi-scale, and not stop looking at pixels, but looking at the entire scene and understanding that to understand the Doppler in one point, you need to understand the full scene because the waves that are causing the Doppler are not generated locally, but they are generated somewhere else. So you need to understand where they're coming from and how to know how they look like at the position that you're measuring. So that's a bit the overview. And then I was going to bore you, which I will, with slides where I try to explain this that I don't. So, but I thought I will try to start with this figure. So this is a TandemX. It's a dual pole TandemX acquisition. So with the 2 satellites, they're doing ATI with a very large baseline. So it's very nice. And they were operating in VV and HH. So there is no cross pole. We only had the HH for the 2 satellites and the VV for the 2 satellites with high resolution and a very narrow swath. It's only 15 kilometers across. And this is Cap de Creus in the Catalan coast, a very nice place to go on vacation. And you can see some things, and they are nice. So you see the backscatter. This is ERA 5 winds, and you see that the wind streaks in the amplitude are aligned with our wind vectors as they should. And you see this small scale modulation. Remember, this is 15 kilometers across, so we're talking about kilometer scale or even sub-kilometer scale modulations in the backscatter. And these 2 figures show the Doppler converted to meters per second in sort of velocities. In VV, which is what you typically have, most of the time we measure in VV because it gives us higher SNR over the oceans, and at HH. And there's lots of things. So we could probably, if we wanted, we could have. I have a few more of these plots. We could have 1 hour of discussion on what we see here because there are lots of things happening. Now, the things that are interesting to see for me is first, there is much more modulation in the backscatter than in the Doppler in terms of high frequency variations. Okay, and that makes sense because the backscatter is dominated by the short scales in your wave, so it reacts very quickly to a change of wind. But the waves don't, because the waves need some time, some distance to develop. So if there is local loss of wind, that does not imply that you have a local loss of waves at longer scales. The other thing is you see things that are problematic. So if you're going to assume that your wave Doppler, that this is mostly it is wave Doppler. If you're going to assume that it is mostly wind-driven, you would expect that if the backscatter goes up, that would imply more wind relative to the surface, that your Doppler would also go up. And that's not always the case. And in fact, you see, for example, a streak over here where the backscatter is going down, implying probably less wind stress, but the Doppler is going up. So it's that if we take a model that would only take the wind as an input and we retrieve the wind from the data, we would get it wrong, right? Unless you believe that is an actual surface current, which it is not. And the other thing that you can observe is that the HH polarized Doppler is different from the VV polarized Doppler, and it's typically larger. And so it's when this one changes sign, this one changes sign too. So they tend to be aligned, but the magnitude of the HH polarized Doppler is always larger than the magnitude of the VV polarized Doppler. And if it is the first time you think about this, it's a puzzle. If you have thought about this a bit more, then you understand this is supposed to be like this. And it's also nice because the difference between these two Dopplers cannot be a surface current, right? Because the surface current is present in both. So the difference between these two Dopplers is 100% caused by the wave contribution. So if you can use this difference to estimate the wave contribution to the Doppler, that you can try to use that to remove it from the other data. And this is to highlight what Johnny was saying. We really need this kind of polarization diversity because it's giving us a lot of information, which we actually do not know how to use. So we can see the information there, but we don't know how to use it. Now, this is a slide from Marcel, who was presenting yesterday. And Marcel is a force of nature. So you should all try to work with him. Which is a good, I think, illustration of what's going on. So we have a representation of the wave spectrum, and you see what contributes to the backscatter. So when we look at backscatter, we're looking at short waves and short scales, and we look at Doppler, we are looking at things in the order of 10 meters. It's a different part wave spectrum. Now, the reason why Roland's approach works very well in most of the cases is because the wave spectrum tends to be well determined. So if you know it here, then more or less you know it everywhere. So going from here to here sort of works, but only sort of works because it assumes that you can characterize the full wave spectrum from one part of it, and that's not really true, right? Because as we were saying before, waves are generated over a long distance, and the short waves are very, very local. So anytime your wave spectrum, the full wave spectrum, does not look like a fully developed equilibrium spectrum, you're going to have problems in the estimation of the Doppler and the correction of the Doppler. Okay, so that's if you agree with this and you didn't know and you know it now, then this presentation was worth something. And if you disagree with that, it's also worth something, because then you will tell me later, and then we will progress in our understanding of the matter. Okay. Now, wave Doppler modeling. I think the title of the slide is a bit wrong, because I think it's the theoretical should not be there. But there's a bit the three ways in which we try to model it, aside from empirical, purely empirical models. These are the three ways we are using. The first one is the brute force way, and I would now insult the people who use it, because it's what I've implemented myself also in my life. So it's, if you don't really want to think too much, I think that's the easiest way you can try. So try to simulate a time evolving surface, which is very difficult, and try to simulate the backscatter for each grid point in your grid, and then simulate what the radar does. And if you do that, and if you do it, you don't have to do it very well. You more or less start seeing the things that you see in the signal. So it works, but of course it works only as well as the assumptions that you make. It's very computationally expensive, and what we see is that it's very hard to simulate surfaces which are heterogeneous. So if you have changing wave fields in your area, it's very hard to simulate. So we know how to simulate surfaces for a fixed spectrum, but if you have a spatially varying spectrum, you can do it per patches. But to have a continuous variation of the spectrum is very hard to simulate. And I also don't think that we know how to simulate breaking waves in this way. And we know breaking waves matter, and I really don't think we know how to model them yet. Now, a much nicer and should say, a big limitation is that we are dividing scales. We are assuming that we are resolving some scales. We simulate a surface up to some resolution, 1 meter, half a meter, whatever you want. But the smaller scales, which cause most of the backscatter, we model with some electromagnetic model. So we are dividing artificially the ocean into different scales, but the scales in the ocean are continuous. So this two-scale division is very arbitrary. Now, it's more elegant to go to these asymptotic or asymptotical models, work by Fred Nouguier, of Voronovich, Mushman. Many people have done this kind of work. And these models, these electromagnetic models, these statistical electromagnetic models, they're very nice, very elegant. You can make them in a way that you do not introduce an arbitrary separation of scales, but we still struggle with things like how do you include breaking waves and these effects in there. They're still computationally very expensive if you want to consider all possible input spectra. So they're nice, but expensive and do not solve all the problems. I was going to show a couple of slides by Fred Nouguier, but I will not, because it's Craig here. Craig, okay. So Craig owes me a couple of beers, because he asked me to introduce SCIM. So I said, okay, I will introduce SCIM for Craig. So now just tell him later that I managed to put some SCIM slides in the presentation, which cost me a bit of sleep time because I had to find them. Well, I'm putting it here because these asymptotic methods, they actually work very well when the electromagnetics are manageable, and that's when you have very steep incidence angle and high frequencies. And that was the case for the SCIM mission proposal, so where you could rely really on these electromagnetic models. And so this is really a slide to advertise that we had SCIM, and SCIM should have been selected, and it would have provided us the first global view of Doppler measurements and surface currents. So this should have happened. And this is blatant advertisement of SCIM, so you don't forget. So there's another slide advertising how this was really a great mission, I must say. But so hopefully it will come back, and hopefully you tell Craig that I had these slides. Okay. The last, I think the state of the art in modeling our Doppler is what I'm calling the Doppler approach, which is how they call it in the literature. Although if you really read the papers by Romeiser, not by Romeiser, by Hansen, by Kudryavtsev, and et cetera, et cetera, et cetera. If you really read what they are doing the same as what Roland was doing 20 years ago, but just adding more components to it. So we are following on a long tradition here and making it more and more and more complicated. But what we're trying to do is to do something which is computationally efficient, which is the same as Roland was trying to do 20 years ago. It's still a two-scale model. We are not doing an explicit representation, or we are not explicitly simulating the surface, which allows us to go quite fast. And it also allows us to introduce components that we don't know how to model, how to really simulate. Because I don't really know how to simulate a breaking wave at very high resolution, but we can model the effect of the breaking wave statistically over a region, right? So we can add these effects with a mix of theory and models in a way that we cannot do with this kind of other models. Now the models are supposed to, so they follow a lot of theory, but inside the models there are lots of parameters that are tuning parameters. So in fact, it's a semi-empirical or a very empirical model because it's been tuned to reproduce the observations. Okay, what happened here? Interesting. You see? Okay, so here there are equations which are not seeing, but which is good, probably. This is very good. Okay. So what we're putting in the Doppler is we are putting different type of scattering mechanisms of contributors to the scattering, and typically we distinguish between specular scattering, which for most SAR systems is not really important. So beyond 20 degrees or something, it becomes quite irrelevant. And then we are considering Bragg scattering, although some of us don't like to call it Bragg scatter. Some people like to call it Bragg scatter. So there's a discussion about that too. I try to call it the regular surface scattering. And then we have the contribution from breaking waves. And okay, it's not there. And for each of these contributions, we distinguish two subcomponents. There is a general drift of the scatterers. For example, for Bragg scatter, you can consider the phase velocity of the Bragg resonant waves to introduce a constant drift term. And then you have the coupling between the longer waves and the short waves, generating a modulation, which would be a tilt and hydrodynamical modulation, which contributes to that. And there are some equations here, but I don't know what happened. Now, the thing is, we have different contributors to our Doppler, which different sensitivities. So they react differently to varying conditions, to varying wind, to different contributions to the wave spectrum. But fortunately, they also have different polarimetric signatures. So if you have a system with polarimetric diversity, you can actually try to separate the contributions to the Doppler and to the backscatter from the different contributions. And that's what we hope to be doing in the future when we have systems that allow for that. Probably there were some equations here too. But it's okay, because the equations was only spoiled presentation. So it's, but not having them when you expect them, it's not so bad. Now, I wanted to go over the different components that we have. And I really wanted to do it to put question marks with all of them. Now, if we take one of the components, this would be the drift velocity of the Bragg scatterers. And if you look, for example, at the last version of the Doppler papers, in that one, they revert to what has been the long tradition of assuming that you have Bragg resonant waves moving the phase velocity corresponding to the Bragg resonant wavelength. And then you assume that you know that because you know your geometry, you know your frequency, so you know the Bragg resonance wavelength, and you know the dispersion relation, so you think you know that. And then the problem appears when the wind is not blowing towards you or away from you, because then you have a mix of Bragg waves going towards you and away from you. And you can assume that statistically they follow some distribution, but I think at local scales, it is very, very random what you have. Right? You may have predominantly waves coming towards you or actually not. Right? So we try to model it. But I think worse than that is that I don't think we all of us really agree that the waves that are generating the resonance scattering are really Bragg resonant waves with wavelengths which are resonant with your radar wavelength, because those are very, very short waves. And if you, so I guess all of you, like me, when you go out and see a bit of wind and water, you look at the surface, and I think what you tend to recognize is that the length of the dominant short scale waves varies a lot and is often quite much larger than the theoretical Bragg scales. And which means that we probably are not really seeing Bragg resonant waves, but we're seeing longer waves, which are non-symmetric, and therefore they have harmonics. And so we are seeing the higher order contributions from longer waves, which have maybe their own phase velocity, which is not the phase velocity of the Bragg waves that would have the scale of your radar wavelength. But these are discussion topics. So I think this is just I want to use these slides to tell you that we have a model for things, but it's very debatable what we put there. And this adds at least 5 to 10 centimeters per second of uncertainty to what we model, a few centimeters per second for sure. If you follow the literature on modeling of radar signals, you see that we're putting more and more emphasis on the breaking wave contribution. The breaking wave contribution is important for HH polarization and for cross-pole polarization. It's less relevant for VV because VV is dominated by Bragg. When you look at the Doppler, however, the importance of breaking waves is larger because breaking waves move much faster than, so the scatterers associated to breaking waves move much faster than your regular surface scatterer. So even if the contribution of breaking waves to the backscatter is still relatively low, because of their very high velocity, the contribution to the mean velocity can be quite high. So the message is breaking waves contribute a lot to the Doppler that we observe. And I hope some of you are very confident that you can model very well how breaking waves behave. I don't. And flying into Svalbard, we had a very nice view of the ocean. And I was looking at the breakers, which are spectacular. And what you see, in fact, is that they first move with the wave that is carrying them, as you expect. But then you see the white cap attaching back to the water and slowing down. So there is a history in the velocity of the breaker, which for me makes it extremely hard to model. What is the velocity of the scatterers associated to the breaking waves that we have? It's some weighted average of the velocity at the beginning, where they're going very fast, and the velocity a bit later on, when part of the white cap is reattaching to the surface. Now, I don't think we have a good model for this. And so we have data, and there's a lot of work going on to try to observe the surface from close by, put cameras, and then link the optical observation of the breakers with what the radar say to try to model it. But we are not there yet. And the question is, how good can we get? Because I think these are very chaotic, very difficult to model effects. Good. This equation survived, which is good. And this would be the long wave. This would be the long wave modulations, and which is, I think, more or less what Roland was modeling 23 years ago or more. And what we have is different modulation. So we have the tilt modulation, So just given by the slope of the waves, which at some point of history people did not think existed, but we know it is there. But I think when we try to model the tilt modulation, we make assumptions. And we try to make the best possible assumption, but there also, I don't think we really know, right? So we can use electromagnetic models to make a guess. We can look at the data, and then we can try to fit the guess we're making to best fit the observation. But there's quite some uncertainty in how big this tilt modulation should be. And I think the same holds for the hydrodynamic modulation. And so we know it's there. We more or less understand it, but its exact contribution to the modulation of the scattering is, I don't think we have a full understanding of that. In particular, considering that what we are finding is that the largest contribution to the Doppler associated to hydrodynamic modulation is through wave breaking. And wave breaking, I think, is the poorest understood part of the entire game. So we have, for me, there are also a big uncertainty. Now, in the models, of course, we can make them work because we have lots of little parameters. We can tune all of them, and so we tweak them until the observations are fitting. So the models are fitting the observations. Okay. So now let's hope that. Okay, let's see. So the questions are all gone. Eh? That's good. It's good because then you can only see pictures, which is nicer. So I go back to the examples that I had before, and what I tried to do here is I tried to so I had the backscatter from VV and from HH, and assuming that I know the ratio of the Bragg contribution in VV and HH, which in principle our electromagnetic models give us, assuming that I know that, I can, from the VV and HH backscatter, I can make a decomposition into the Bragg contribution for both polarizations and the non-Bragg contributions for both polarizations, which would be what we could associate to specular scattering, which is very little in this case because of the incidence angle of 41 degrees, and contributions from breaking waves, and from whatever you tell me that is not polarized. And so, and what I show over here is the ratio between this non-polarized scattering, mostly breaking waves in the model, to the total backscatter in one of the polarizations, and this one in the other polarization. So you see some data there. And here you see again the three Dopplers that I could play with. Maybe I should not show all of them. So you see the VV Doppler, the HH Doppler, which is different. And in this case, you could actually also do cross-correlate the return and VV polarization at one time with the HH polarized signal at a different time. So you could do an interferogram with a combination of polarizations and look at the Doppler you get there, which is again different, but I don't really understand what it means. But this is the setting. And then what we can look is at the difference between the Dopplers. And the difference between the Dopplers is actually very nice because it's actually very, very smooth. And that's more or less consistent with what you expect, right? Because you expect the wave field to be statistically more homogeneous than the wind field. And if the wave Doppler is caused by your waves, that you would expect that the difference between the wave Doppler and different polarizations, which are all wave-driven, should be relatively smooth. And that's what we see over here. So we see the difference over here, the difference for the other weird combination, but doesn't matter. So what we were trying to do in this example is to see if we could actually remove the wave Doppler by combining these things. This I already showed in the first slide, the fact that we have places, but it's a nice one to discuss. So this is what I showed before. We have increased Doppler in a place where we get reduced backscatter, which would be counterintuitive if you did not account for different scattering mechanisms. What you see here is that the ratio of the non-polarized scatter, which was what we think breaking waves to regular scattering, to your Bragg scattering from regular waves, has increased. And that sort of makes sense because the regular scatter is driven by the local wind, but the breaking waves to some extent is the reminder of the waves which are still there. So the waves which are still there, they're still dissipating energy, which means they're still breaking. And because the wind, the instantaneous wind has reduced, you have an increase of the relative contribution of the breaking waves to the non-breaking scattering. And now, because of the Doppler associated to the breaking waves is much higher than the Doppler associated to the non-breaking waves, when the relative weight of the breaking wave increases, which is happening here, you can expect to see an increase of the Doppler. Yeah? So this Doppler is an expression of the increased weight of your breaking waves in this region. Yeah? So this explains why you have this kind of why you have this kind of signature. Okay. So that's to illustrate what we are seeing. Now, this is not really the purpose of today, because the purpose of today is to show you how little we understand. But this slide is to illustrate that by using this polarization diversity, we can try to attempt to clean up the wave Doppler without anything else. So what I did over here is I put in a model, and I also tried with neural nets, but they give more or less different results. For the model, I tuned some parameters so that things worked as I expected. And what I was using is the Doppler difference and the backscatter and the polarization ratios as an input to a retrieval, where I use them to estimate the wave Doppler in the VV polarization or in the HH polarization, and then I was subtracting that wave Doppler from the total Doppler and then looking at the residual. And this is not super great, but you see that in a quite simple procedure, we are getting rid of most of the Doppler that we see. And you expect that Doppler should be more or less zero because there are no strong currents. So we get rid of most of the Doppler, except in some places with some artifacts. And here you see, for example, something that we actually already recognize in the amplitude image. So you see a very nice eddy close to the coast. And here you see they look like river plumes, and there is a river here. So I think there is more or less coming from the river. And this I don't know. But the point is that by combining polarizations, you can actually do a decent job at estimating the wave Doppler and removing it from your data. Now, some examples of implementation of the Doppler. So for harmony, we have a scientific workbench which is open source. So if you are interested, you can download it and try to run it. And we are giving different scenes. In this case, we were taking an LES wind field for a simulation over the Barbados associated to the Eureka campaign of a couple of years ago. And in this case, we are simulating a cold pool. So you see atmospheric front. In the green is the surface moisture. White are clouds. And if you look very carefully, you can see some red points in the image. This is rain in the LES simulation. And if I animate this, you can see so this. I think it's worth attending the presentation just to see this animation. What you see is that there's a mean flow. In this case, I don't know, I think 10 meters per second or higher. And here there is a downdraft associated to the precipitation. And then you have a stream of cold air flowing back in the opposite direction to the main stream, which you see over here. So you see the surface moisture, which you can use as a tracer of the wind. You can see that it's moving in the opposite direction as the mean flow, which means that the total surface wind is much lower here than around the cold pool. And so we take this wind field as an input to our Doppler rim model. We assume there are no currents in this case. That's our assumption. And then we produce, for harmony's case, the backscatter at the different polarizations, but I'm only showing the principal polarization, which would be, VV and a strange polarization for the harmonies. And then you see the Doppler at the same polarization for the harmonies and for Sentinel-1. But you see here, this is a bit of harmony advertisement, is that the harmony Doppler is less noisy than the Sentinel-1 Doppler. And that is the case because we have an ATI system. And so we are doing a long track interferometry with a short baseline, but it's still much better than doing Doppler centroid anomaly estimation with a single phase center. And but this would be the inputs that we would then try to put in our retrieval. These are the outputs of the Doppler rim model. And here what you see is the estimated wind field, the inversion that we have prototyped for harmony, and the estimated surface current field that we would get with harmony. And then what you see is that, and today is all about showing problems, is that on average it's okay. So the wind field that we retrieve is not too bad. It's a very high resolution wind field, so it's a couple of kilometer resolution, and it looks quite okay. And here you're seeing the relative error of the estimated wind. And you see that for the estimated wind, we are having issues on the areas where there are strong gradients, where the wind field changes very quickly. We have trouble inverting that. And for the Doppler, you see that away from those regions, away from the fronts, we are retrieving more or less a zero current, which is what you would expect. So we are compensating for the wave Doppler in our simulation correctly. But around these large, strong wind gradients, we are suffering because we are seeing strong residual Dopplers in our retrieval. And that's because we are failing to, from the data that we simulate, we're failing to predict the correct wave Doppler and to subtract it from the data. Sometimes we are overcompensating for a wave Doppler. And this has to do because our estimate of the wave Doppler uses all the observables that we have, including the wind. And the wind is responding very quickly to the wind forcing, but the Doppler is responding less quickly. So when you drive partially your wave Doppler model with something that changes very quickly, but which is related to something which does not respond as quickly to this change, then you end up with an error in this transition region. And so these are things that we need to learn how to improve. And I think listening to Artem, I think I already have some ideas on how to go about this. But this is a bit the status of affairs. And then, yeah, we should stop in a couple of minutes. I wanted to, I have two slides that I want to show. And this is also from the harmony, this is in the ATBD of harmony for the retrieval of surface currents. Then I don't want to go in detail, so it's a nice diagram that we did for it. But what I wanted to highlight is that what we're doing often in all our missions is we're trying to do the retrieval locally. So we're looking at information that we have locally. So we have backscatter, we have Doppler for different polarizations. We may have estimates. We have some spectral information. We have the IMAX parameter. So we know something about the waves. Not super good, but we know something about the waves. But we try to typically do it at pixel level, right? And what we think we have to do is this. There is a scheme, and I think we got away with showing this to the Advisory Committee for Earth Observation, and still, after seeing this thing, they selected harmony for implementation. It's not bad. And but this is what we think we have to do. So we have to go towards this, also what was said a couple of times yesterday, towards this multi-scale integrated retrieval, where acknowledging that everything is related to everything, and at all scales. And for example, if we are looking at, today we're talking about the Doppler. If we want to retrieve surface currents, then of course we need to first remove the wave Doppler from the observed Doppler after calibrating the measurements. But for this wave Doppler estimation, you really want to take everything you have. So you want to take estimate the surface stress or your surface wind at multiple scales, because that is driving the waves to some extent. But you also want to, for sure, take any wave information you have retrieved from the data itself. So if you have wave spectra estimated from the data, then you have to use that in your retrieval. to estimate the wave Doppler before you try to subtract it. And this is actually what Artem is starting to do, so that's very nice. But I think this is and it goes also in the opposite direction. So you really need the waves to correctly estimate the surface stress. And so everything is talking to each other. And if you have more instruments, then you also need to use them in combination with your radar to do your retrieval. So I think this is where we have to go towards, this integrated, multi-scale, complicated things. And that's almost my last slide. I will close with this one. This is a slide that I made years ago for a precursor study for SeaSAR. It was when ESA was running these ocean surface current mission studies. And I prepared the slide for that. And I think it's still, I think it's a good slide to also end. So if you try to estimate surface currents, you want to look at what are the contributions to your error budget. And then we have, so we have measurement noise, we have geophysical noise, and then we have systematic biases in the instrument, and then we have geophysical bias terms or contributions terms which you don't want to have, like the wave Doppler. And I think what I wanted to say with this is that when we design new missions, we put a lot of effort in solving the things that we know how to solve. And we know how to solve measurement noise because I can ask Martin Suss to make me a better radar. And if I give him more money, he gives me a better radar, right? Then you go to Airbus and say, okay, you want this measurement noise? Give me 100 more million, and we'll do it for you, right? And that's a bit dangerous because we put a lot of effort into reducing this thing. We can sort of deal with a bit of the geophysical noise by averaging spatially that maybe constrains the resolution of the product, but you can deal with it. From the hardware point of view, systematic errors are really, really, really tough. And I think we have to learn to deal with them both by learning how do we deal with data which contains systematic errors. So I think if we keep telling Airbus or whatever industry, give us error-free data, then we will get very high bills and it will still not meet requirements. So we really need to learn how to deal with it. And for me, we need to ask ourselves, when do we need data without biases? Because if I'm interested in vorticity or divergence, then I don't really care if there is a 2 meters per second offset in the surface current because I'm only interested in the derivatives. So I think when we discuss requirements, we really have to think hard about what do we need. Are we interested in relative motion? Are we interested in absolute motion? Because this leads to totally different challenges for people implementing the missions. But the main thing, and I think that's an important thing to understand, is that in the end, the performance bottleneck is going to be the inversion. It's not going to be the instrument, but the inversion. So we can optimize the system as much as we want, but in the end, it's the inversion which is going to limit. And that means that if you have to make choices in the design of a system, then you should not look only at how do you make the noise better, but you should look at how do I make the inversion easier for myself. And for me, that means, for example, that we want to have dual polarization or quad pole, because that's helping us dealing with the non-current contributions to the problem, right? Much more than going for the best possible noise, because we will you can go to 5 centimeters per second from a noise point of view, and we are still dealing with tens of centimeters per second because of the unknown contributions to the Doppler. Okay, so that's my last message. So I hope it sounded very confusing because that was the purpose, remember? So, yeah. I think you need a microphone. It's going.
Can you show this rain picture again?
The LES simulation?
Yes.
Yeah. No, he wants to see. He wants to see.
Yes, my.
Oh, okay.
Yes, this one. So you show there to the upper one that is apparently a rain signature, right?
You have the, I don't think we're seeing directly the rain, but what you have
No,
is.
on the right-hand side. So that is an NRCS image,
It's
right?
an NRCS, but it's not the rain. So we are not modeling the rain in the simulation. We are only modeling the effect of the surface wind.
Yeah. But it could be these bright streaks you see there in the image that could not be a surface effect. It could result from volume scattering in the atmosphere.
Yeah.
So it has nothing to do with surface movement. And I think you showed another image, the Doppler. That is the Doppler, right?
Yeah, but in the Doppler, this is modeled. Yeah? So
yeah, and it shows also anomaly in the area where you, yes.
No.
So if you compare them, the upper ones are NRCS, right?
Yeah.
And the lower one is the Doppler, right? And you see these bright streaks there or patches. They have a correspondence in the Doppler map, right?
Yeah.
So what is the explanation?
In this case, we know because this is a pure simulation, and we don't put the rain in the simulation. So the rain is in the LES, but it's not in the radar signal simulation. So this is really increased surface roughness. I agree with you that in reality, we may be seeing, if the rain is strong enough, a contribution. But the contribution of rain to the backscatter is very complicated because you have attenuation of the surface,
yes,
and you have contribution
but we
for the volume.
published a paper on that. And looking at radar signatures of rain, of convective rain cells, especially, and that is convective rain here. Yeah. And so these bright spots we have identified as coming from volume scattering at hydrometeors or in the melting layer.
And what frequency
so
was that?
They have nothing to, they are not a surface signature. They are a signature that comes from the atmosphere. So, and this is completely decoupled with the motion in the on the ocean surface.
If that's the case, I would agree. In the simulation, it is not because we don't have it. In reality, maybe. I don't know. I think
you can the data you show are Envisat data.
No, this data is simulated.
What?
This data is simulated, and the other data that the real data that I showed that was TerraSAR X, so that's X-band, where you would see much more rain effects.
But if you have cross-polarization data, like you have it in Sentinel, you see, then you can identify these bright areas very nicely, that they are not surface signatures, but they are signatures from rain in the atmosphere, and especially in the so-called melting layer.
Yeah.
That is well known from people who analyze data from ground-based radar. So yeah, there you get, they call it what is it? The bright layer, because there the radar cross-section is much increased.
Yeah. We can discuss this maybe later, or maybe in the breakout, in one of the breakout sessions. There was a very nice PhD thesis by somebody at IFREMER, where they were comparing coastal rain radars with SAR images, and they tried to model that, and it was actually quite complicated. And because the rain may increase or decrease the amount of backscatter depending on how much it rains, but we can discuss later. There were questions in the, okay.
Yes, thanks, Paco. Very interesting presentation. Can you go to the last slide?
If I go to the real last slide, I'll
that
show you
one,
new material. This one.
This one, when it's filled in total. I think this will become a highly important slide for the recommendation. And particularly when you put on the last bit of box on it, which was the inversion. And I want you to consider with the inversion one thing, and that's the need for improved in situ observation. And we have to have this as part of the recommendation, not just for the Doppler, for all of the areas of the themes we are discussing. And it is one of the major reasons why we are still not advanced enough with these fantastic instruments, because we haven't had proper in situ observations at the same time as a satellite acquires the data. And it's not that you do this in a 2 weeks campaign. That's absolutely just to sort of fail immediately. It has to be consistently over long periods. This is a message that ESA will have to receive from us. And hopefully one day they go ahead and we create the super sites.
I think we agree with that, right?
I've been informed that the copy is ready, so if you have a couple of questions in the chat.
Yeah, should we look at the questions in the chat?
I know there are.
Je sais pas, on a une autre question, pardon.
It was very clear, says Paco, says Art. So Christine likes it, that's good. Yeah. I think that, I don't know if you can read the message. No, you cannot. Christine is making a good point. There's a very optimistic view on this, which I agree with, is that in altimetry, you altimetry people have dealt with assisted bias for years, and you're doing a very good job, but it's taking years. And I think we are in the same situation with Doppler. So we have a difficult contribution. It's harder than the assisted bias in altimetry, because the wave Doppler is actually the dominant component in the signal. So it's not a small thing to remove. It's the biggest part of the signal. But we have many years ahead to deal with it. So I agree with that. I don't know if there's more questions. I don't know. Any more questions for anybody? Yeah.
Yes, one. Yes, thanks, Paco. I think you did a very good. I believe so.
I did a good job at sounding confused.
So you perfectly go from the good to the bad and then to the ugly along your presentation. So we think I thought I saw some. I think I knew something about this. And then at the end, I was as lost as you, I believe. And because we already had the problem with cross-section, we don't really know what's scattering. And then we multiply them with some velocities that we don't know where they come from. And then at the end, we don't even know what is the scattering at the end, because it starts to be some breakers. And everything with this, we do some Doppler that we want to measure. And at the end, what for is just to remove it from what we measure to get some cinematics, some currents below. And so I was wondering, is Doppler actually a good measure that we want to play with? Since then we need to deal with other calibration stuff and so on. So I start to believe that it's not a good measurement to do what we want to do, which is getting some geophysical measurement. And I say, okay, is there something else that then we can do? And if we look to other data like optical, we don't have any of this problem. We don't have any waves Doppler. We don't have any strange velocity removal to do. And can we do, since SAR is doing a super high resolution, and since we can see the waves, can we do an optical way of measurement, which is much easier and much faster, and without these weighting velocities by cross-section? Because actually, if you do some only small time separation between two detected measurements, we only deal with cross-section, which is much easier, and you can do much better, I believe, much better current estimation.
And that's a question you want an answer, or you want?
Since we identified so much problem in Doppler, so can we move on to something just as easier and much more secure?
No, I think that it's a good point. And I made the slide which I didn't want to show because I knew I would run out of time. But it's, what do we do with it? So Doppler is there, right? It's a good signal, and it's a very strong signal, which does. So we should not say, oh, Doppler is bad. It's a good signal. The question is, what do you want to do with it? Then we know, and Roland has shown many good examples where we can retrieve surface currents. So for strong enough surface currents, it's a very nice measurement of surface current, because then we manage to clean the part. Now, I agree with you that I don't really know how good it's going to be. I don't know. And I don't think anybody really knows. So this is going to be a work in progress, and we will see how far we get. And I think that one of the big problems we have is that we always start this adventure of making new missions in the let's measure something approach, right? To say, oh, let's measure surface currents, or let's measure wind, let's do something, right? And we always confronted with the fact that we never measure that what we want to know, right? We measure backscatter, we measure Doppler, right? We do not measure currents, we do not measure wind, right? Now, for me, what we have to move more and more towards is to stop trying to retrieve particular variables, but really go towards an assimilation point of view, right? Then I think we can learn how to forward model these things so that we can use the observations to constrain the full model, right? So where you constrain at the same time your stress and your current, without really trying to say, I have the current and I have the stress, but you can constrain both with the observations. But I think this is not only for us. So I think if you look at the biomass mission, it's the same problem, right? They say we're going to measure biomass, but you are measuring backscatter. So the only thing you can do is constrain the biomass with the backscatter, and you need to add information coming from other places to get to the biomass. So that's a general problem, and we always struggle because we promise the community level 2 and level 3 products that are easy to digest, right? And that's, I think, where the problem is. But I think to some extent we will get surface currents. The question is, what is the quality of those? Then will we ever reach 10 centimeters per second as we are sometimes promising? I'm skeptical, but I think we should try. And we may manage, and we may not, but we should learn how to use the information in different ways.
Okay, I'm going to interrupt you there because I have a nasty feeling that you're going to talk through the whole coffee break if I don't do this. So sorry. Yes.
I would.
Yeah, I know. Thank you very much. It's going to be a good breakout, this one. Yeah, later on. Yeah, so there's coffee outside. It's going to be 15 minutes. So back here, 10:38.